Hello, class. Happy week 11. It's me, Prof. B, down here in the corner. Um, so, wow, this is kind of like the end of the road, so to speak, because this is the last week of actual content and learning. Our final assignment um, is due this week, and then after that, it's just a final exam. And thank you to those who submitted the critical article review assignment. You're brave people for doing so. Anyhow, so what I thought I'd do, thought I'd combine this in weekly last course announcement with a tutorial on what you need to do for this remaining problem set 5. That again is a quiz within the quiz menu within Leo. So I'm just going to crank through some screens here. The data that I have up on the screen for each problem is slightly modified, but similar to what's actually contained in the data sets that you need to download for the series of questions. So there's like 3 or 4 different data files you need for the set of questions. So the very first question one, it's an ANOVA question, and it's the only ANOVA question you're going to have to do for this problem set, and it's actually pretty easy. So it's asking you to compare 3 different instructional groups or approaches, and conveniently the data is arranged here in 3 different columns, and I have prefaced this before. Anytime you run an ANOVA within Excel, your data needs to be arranged into columns such as this, where each group is its own column. Not to say if you used other statistical applications, it doesn't have to be set up like that. It could say one column could be the group name, and then the second column could be the actual data for it. So it actually could be 2 columns. Does that make sense? But Excel, requires you to have your data into groups. So the question you'd ask, why are we doing ANOVA? It's not because the problem is telling you to do so. It's because there's 3 groups to compare. So that should be your cue that I'm not running a t-test or a z-test. I need to run an analysis of variance, or ANOVA, because there are 3 groups to compare. And there's an independent variable, which is the instructional type, and a dependent variable, which are these scores here. So right there, that's why you should know, okay, I feel confident I'm doing ANOVA. So you're going to get some output that looks like this. To get to this output, if you haven't learned this already, you simply just go up to the data ribbon up top here, go to data analysis, scroll up to the top. It's the very first analysis tool, ANOVA single factor, and all you got to do is just highlight your data and check the box for labels in the first row. Now here's the important piece. Change your alpha here, because even I made this mistake when I first ran this data. I left the default of 0.05 in, and I went and I analyzed it, and I was like, what? But you actually go back, change this to 0.01, and then put the data in wherever you want. You can put it into a new worksheet or an existing worksheet. You click OK, and boom, it's done. So what you need to pay attention to on this output, a few things I've highlighted here, okay? First of all, you always get this summary table, which gives you the averages for your groups and variances. You want to look at your F value. This is your calculated F, and this is your table critical value F, okay? You want to look at those 2 things and say, okay, are one's bigger than the other or smaller than the other? We see that this number, the calculated F, is smaller than the critical table value, so guess what? We have a non-significant finding here. But in practice, a lot of people don't even look at that. They actually look at the p-value, and we see that 0.41 is greater than, what was our decision rule? 0.01? Okay, so we know it's not significant. So what does that mean? It's basically saying that the averages between these 3 groups are statistically non-significant. Even though there's a difference between like 5 on a couple of them, it's still statistically, it's not enough. And granted, I'll tell you why it's not statistically significant. It's because of the sample size. It's small. Okay, so questions 2 to 5 tell you to make a pivot table and then some subsequent chi-square analyses. The pivot table, again, we've done this before in prior discussion activities. All you need to do is click Insert, go to Pivot Table in the left corner here, select your data, which I already have it, and then click OK if you want it in a new worksheet. And to build your table, let me move my little video over here. You got to make sure one of these boxes is a row, another one is a column, and it doesn't matter which. You only got two variables here, which one you grab, either gender or type, and drop it in the values box, and boom, voila. You've got your pivot table. Yay! So it's these 4 cells in the middle that you would need for your chi-square analysis. And that's it. So you can literally take the numbers from those 4 cells, drop them into the chi-square calculator, which you received from me. And the calculator does all the work for you. Or you can go to that website I gave you as well from last week as well. It'll do the same thing. So what I like about the calculator, it gives you the expected frequencies, but the formulas, okay, when you click on each of the cells to see how those expected frequencies are computed. And again, this analysis is comparing the observed against the expected frequencies. Remember, this is huge. Change your p-value to 0.01 because the problem's telling you to do that. And again, this is a chi-square because there's 2 categorical variables being compared here. So you've got the gender and type of animals, dog, cat, male, female. 2x2 contingency table is what this is called. Very appropriate for a chi-square analysis. Okay, and basically same thing, compare your chi-square test statistics that's calculated against the table critical value. You see that it's smaller than that, so that's going to be non-significant. However, the calculator gives you a p-value, again, decision rule 0.01. This thing is obviously much bigger than 0.01. Non-significant, so do not reject the null. It obviously tells you to do that, but it's telling you to do that because this is greater than 0.01 and this is smaller than this number. Make sense? Now, I'm not happy with this particular set of questions, particularly the data, so I just want to preface that you would not do a chi-square analysis on a 1x6 contingency table that you're given here. I don't know what my colleagues are doing. Many times I've complained about this problem. But yeah, we have got 6 days of information. Yeah, days of the week are categorical, don't get me wrong. But day sick is a count. It's a numerical quantitative count. So this would not be an appropriate chi-square analysis. So all you need to do is plug in the numbers here, and the way this analysis is being run, it's comparing each of these values for each day against the average. Okay, so if I took this, the average down here is 10. That's how I know. And I compute the expected frequencies simply by dividing all my calculated values here, and the chi-square that you get, and obviously you'll have this worksheet, is you just sum these up and you'll get a chi-square value of 0.6. Okay. Degrees of freedom is 5 because it's just n minus 1. There's 6 days here. Minus 1 gives you 5. You just plug this into the chi-square INV function. You just put in this is generic information, so you know your probability is 0.05. You're assuming that because it's not given in the problem. There's 5 degrees of freedom. Boom, you get 11.075. The p-value, chi-square dis.rt function, again, you just take your calculated chi-square value, which I showed you is the sum of those values, your degrees of freedom, and it automatically tells you what your p-value is. So guess what do you need to do? Again, we always compare our calculated chi-square value against our critical table value. We see that it's smaller than that, so that means it's not significant. Also, we see that our p-value is 0.98, which is obviously much bigger than 0.05. Again, not significant. Do not reject the null. So that is that. So you'll have that. Again, not happy with that problem. Now, the last set of questions are asking you to do a correlation and regression analysis. Again, I got some beef with this set of data as well. Sorry to be so picky, but I would never, ever, ever, ever abbreviate my data because of place value. So we have advertising costs in thousands because someone's too lazy to convert this to thousands. And then we have number of orders, our dependent Y variable, in millions, again, because someone's apparently too lazy to actually convert this to millions. This is what I put on the right side of the screen. And I'm just telling you, if this was you, this was me, and I was actually running this data for my employer, supervisor, boss, contract, whatever, this is actually how I would format my data. I would actually have it say $67,930 or 5,902,000 orders. I would not say 5.902 or 67. I mean, and let me tell you why. Not only do you have to do that, you ended up having to do the calculation afterwards on the result because you're not going to tell your employer, boss, or whomever that it's 67.93. Oh, by the way, convert that to thousands, or express the orders as 5.9. You're just not going to do it. You're going to do the calculation anyway. So why not do it from the get-go and have it be consistent on the output as well? So with that, we're going to be consistent with the problem though and run the data as is. So we have our X, this is our independent variable, our Y, or our dependent variable. Now in a correlation analysis, you don't care which is X and Y. Because you can see, if you look over here, I can run a correlation analysis just by using the equal sign CORREL function and say array 1 and array 2. Excel doesn't care what data is in what, your X or your Y is which array is what. However, when you run a regression analysis, which is the same thing when it's only two variables, and there's two quantitative variables that you're analyzing for a correlation analysis, the regression analysis gives you the correlation, but then it gives you some extra information if you are specifying a direction, if you have a hypothesis that one variable is influencing the other. So with that, to run the regression analysis, again, we just go to our data tab, data analysis, we scroll down to regression and click OK. It asks for our Y. Okay, so we know that that is this column, or number of orders in millions. It asks for our X, which we know is our advertising cost in thousand. Since we have selected all the data, we check the box for labels, and then you can put this anywhere you want. Okay, so you click OK, it'll run it, and you'll get an output that looks like this. Okay, and I highlighted it so you have some things to pay note of. Your multiple R, guess what? This is the same number as that correlation I ran over here. Now, it also gives you this R square, which is this number squared. This is also called your coefficient of determination. It's also the way you interpret it as the percentage of variance accounted for in the dependent variable by your independent variable. That's a mouthful. So in this case, using this data, it says there's 16%, 0.16, of the variance in the number of orders can be accounted for by the cost of money spent in thousands in advertising, to put that in context. And another number my colleagues are interested in you knowing is your standard error. This is the variation around the regression line and the units of the dependent variable, which is the number of orders. I personally don't ever pay attention to standards of error, but whatever, my colleagues do. So it also gives you an ANOVA output, which is interesting because this is saying, hey, if you were to analyze this data using the ANOVA model, you'd get a significance value and your calculated F value. Now, when you run this data, which is a single variable in regression, you're saying which is X and which is Y. This F value is going to be the same as this p-value that's in the ANOVA table is going to be the same as the p-value that's down here. Now, if this is what's called a multiple regression, there would be more X variables or more independent variables, and hence that's where the p-values would change. So just for sake, you know that these two numbers are identical, okay? But what you need to pay attention to when we see this p-value is 0.08, we know it's not significant. It's greater than 0.05 and 0.01, our typical thresholds. However, to understand the regression analysis is to understand the regression equation, which is y, which is a predicted y value equals the intercept plus your slope times some predicted x value. So you can get all this information directly from the table that's given to you. So we know that our intercept is 2.086. We know that our slope is 0.035. If I just plug these numbers into the equation, I get, using a predicted x value, and you can pick any number here. I just randomly chose $81,000 worth of advertising. It is predicted that 4,954,000 orders would be produced. So that's the regression analysis. Pretty easy breezy. It's basically an extension of the correlation, which you infer a direction and specifying an independent and dependent variable. Okay, folks, that's it. That should be enough to get you through this last homework assignment pretty easily. And again, I will give you this question 6 through 9 template as well. So, all right, folks, let's have a great week. Any questions, just ask.